I'm talking about index pairing and scattering theory. And so this is work in my PhD thesis at the University of Wollongong, supervised by Adam Rennie, Alan Carey, and Alex Mundy. So I am aware that most of you are not familiar with scattering theory. So the bulk of this talk will be setting up all of the definitions from scattering theory that I need. And once I do that, there's some particular operators of interest in scattering theory. So one of them is the wave operator and the scattering operator. And so I'll show that the wave operator for Euclidean scattering has a very particular universal form. And this form actually allows us quite easily to view or to construct an index pairing which computes the number of eigenvalues of the operator we care about. And so this can be seen as sort of a topological interpretation of a well-known quantum mechanics result called Levinson's theorem. So the picture to have in your mind for scattering is a particle comes in from one direction, interacts with some obstacle or a potential, and then it scatters off as a different wave. So just keep in mind, after the interaction, there'll be a different wave to what you started with. The scattering theory of physics is just concerned with how particles behave before and after interacting with each other. And so the mathematical way of dealing with this is perturbation theory. So the history of scattering theory is basically the history of perturbation theory for linear operators, self-joint operators. And so mathematically, the problem that we set up is we have two self-joint operators, H0 and H, acting on some Hilbert space. And we want to be able to compare them in some way. So usually we want H0 to be what we call the pre-Hamiltonian, and it's usually a much simpler operator than the operator H, which is we call the perturbed Hamiltonian. And we want to use information about the spectrum of H0 to determine information about the spectrum of H. So throughout this talk, I'll just be dealing with my H0, the simple operator will be the Laplacian acting on L2 of Rn, and my perturbed operator will just be the Laplacian plus some function v. So I'll need to assume that the function v is real, and it has to satisfy some kind of decay condition for all of my theorems to work. So I say here that I want my absolute value of v of x to decay like 1 plus the size of the norm of x to the power of minus rho for some rho bigger than n plus 1 on 2, when n is the dimension. This is actually not enough for some of my theorems, so later on I will point out that you need more decay for some of my results. Okay. So, as I said, scattering theory is concerned with the spectrum of the operators H0 and H, and so some standard assumptions are that H has a finite number of eigenvalues and H0 has no eigenvalues. And for the operators I described, this is well known. So the Laplacian has no eigenvalues, it has purely absolutely continuous spectrum, which is the positive half line. And the perturbed Hamiltonian here, given our assumptions on the potential, it will have a finite number of eigenvalues, each with finite multiplicity, and they are all negative or 0. And it has the same absolutely continuous spectrum as the operator H0. Okay, and so I use the term down states for eigenvalues and sort of interchangeably, so I apologize for that. Okay, so yeah, the point of scattering theory is usually we can't actually solve any of the equations of motion for a more difficult potential. It's not very easy. And so even for a really nice function v, like there are not many potentials that you can actually solve these equations of motion. So the starting point of scattering theory, so first of all, each of our operators is self-adjoint. So by Finite's theorem, they're going to determine a one-parameter unitary group. And so I've just called u of t and u of t. And so the naught throughout this talk will just refer to the free guy, and anything without the naught is the perturbed guy. All right. So building up to my first definition in scattering theory, if we have an element of the absolute continuous spectrum of our Hilbert space, so the absolutely continuous subspace of a Hilbert space for the perturbed guy, we, for physical reasons, expect that a long time after the interaction, we should be able to approximate the evolution of this state by the evolution of a different free state, which we call psi plus. And a long time before the interaction, we should be able to approximate it with a different free state, which we call sign minus, and there is a sign minus. So yeah, we can package this into one definition. Our first definition is scattering theory. So if we just use the unitarity, put both operators on one side, take that limit, we get this definition. So the wave operators associated to this pair, and so they're defined as the strong limit as p goes plus minus infinity of either the ITH, either the minus ITH naught, and the projection of the absolute continuous spectrum of H naught. And so whenever I use this notation, plus or minus, it just interchangeably, it's two equations in one. So there's the plus infinity and the minus infinity, and they're two different operators. All right. So one may ask, do these operators actually exist at all? And so it's well known for our situation. So even with very little decay, just rho bigger than 1, that these wave operators exist. And actually, we know a little bit more than that, but this is enough for the purposes of today. So yeah, any textbook on scattering theory will tell you this fact. So the key to analyzing these wave operators is to look at them, consider them in the right space. So as it says here, the Fourier transform, we've looked at this before, it's a unitary operator and it diagonalizes our Laplacian, but not in the right way, not the way I want to use it. So when you conjugate the Laplacian by the Fourier transform, you get multiplication by the norm of the variable squared. And what we really want is just multiplication by the spectral parameter. So if you change to polar coordinates and do some rescaling to make things nice and unitary, you can define a new operator, F naught. It starts from L2 of Rn and goes to L2 of the half line, tends to L2 of the sphere. And this operator, so it's basically just rescaled Fourier transform, and now we split into polar coordinates. And if you conjugate the free Hamiltonian, which is the Laplacian, by this F naught, you get multiplication by the spectral variable. So this is the diagonalization that we really want to use for scattering theory. All right. And so the wave operators actually satisfy some nice properties. And so if you apply the wave operator to the Hamiltonian, then it commutes through at the expense of it is now the perturbed Hamiltonian. So it's been called the intertwining relation. And this sort of makes physical sense. Sort of takes in a free state to a perturbed state, and so it makes sense that which operators are in each position. Right. And we can say more, wave operators are actually Fredholm operators, and that they're partial isometries. And so if you do W plus minus, adjoint W plus minus is an identity operator. If you do it in the other order, then you get the projection onto the absolutely continuous spectrum, which, given our assumptions, is actually just an identity operator minus projection onto the eigenvalue, so the point spectrum. Right, and I realize that I've not written what S is. So we can define an operator called a scattering operator. Right. So I'll just put it here. So S is W plus adjoint W minus. And so this operator is meant to take in a free state before the interaction and spit out a free state after the interaction. And so based on the intertwining relation, this scattering operator is actually going to be unitary and will commute with our free Hamiltonian, so the Laplacian. And so this means that in the spectral representation, we actually get a family of unitary operators indexed by the spectral parameter that acts on the sphere. Okay, so just a simple example in one dimension to keep in your mind maybe. We can consider in one dimension we have the Laplacian is just minus the second derivative, and our potential here is going to be just for a square well, so it just inside of a finite region it is a negative value, and outside of that region it is 0. And so this is one of the very few well-known ones that you can actually explicitly solve all the equations of motion. And so in this case, so we have the scattering matrix. So the scattering matrix is going to be a unitary operator on L2 of the 0 sphere, which is just 2 points, so we get a 2 by 2 matrix. And it's not a particularly nice form, but it is very explicit. So there's a couple of features that make of interest. So I call this a scattering operator. It's all about scattering states, which are about long after or long before interactions. But this operator, if you knew all the eigenvalues, you can actually check that if you plug in I times an eigenvalue, you find that at each one of these values, so for each eigenvalue, you have a pole on the imaginary axis corresponding to that. So this scattering operator is somehow sensitive to the eigenvalues, which is perhaps not obvious that there's point spectrum information in this operator. Okay, and also there's also perhaps not obvious, but if the parameter L and the parameter E naught were very particular values, so if the square root of E naught times L was a multiple of pi on 2, say, then as you sort of approach 0, you get weird behavior. So you get the determinant of this is almost always -1, except in this strange case where the determinant is 1. And this corresponds to the existence of a weird kind of solution, which will cause me having issues later on. So I'll describe these. So they're called resonances. And so if n is not equal to 2, we say there's a resonance at 0 energy if there exists some psi which is L infinity, so some bounded function that is an eigenvalue at 0 in some distributional sense, so usually in some solid space. And if n equals 2, there's a particular strange thing that goes on. It's something called a p-resonance, and the definition is not so important, just it causes me some great issues later on, so I have to exclude this case in my theory. So this is why I point this out, that in certain situations I cannot actually handle this behavior. So I'm trying to. So I did mention at the start of this talk Levinson's theorem. So Levinson's theorem, it's a well-known theorem of quantum mechanics, and it tells you a relationship between the number of eigenvalues of your system and some scattering behavior. So the original one is 1949, and it tells you that for some nice enough potential V, the number of eigenvalues counted with multiplicity, so the number of downstates, is given by 1 over pi delta of 0 minus delta infinity, where delta is phase shift, is determinant of the scattering. And I've written in brackets here plus a half. And when you get this weird analytic behavior at s equals 0, these resonances, you get a plus a half in your formula. And it's very strange. So going back to our wave operators, we can actually sort of immediately get an analog of this Levinson's theorem as an index theorem just by using the Fredholm property of our wave operators, but it's perhaps not so interesting. It's not sensitive to this resonance behavior at all. So if our potential decays fast enough, so this is very bigger than n plus 1 and 2 I said earlier, then we can immediately just compute the kernels of W minus and its adjoint, and you find that the dimension of these is equal to the trace, so the number of eigenvalues of the trace of this projection onto the point spectrum. So there is index data in here already, but we want to capture it in a different way. So our next sort of section is describing the wave operator having a particular form and using this to detect this index data. So to do this, I need to introduce a few more operators. So the dilation group acting on L2 of Rn, just given by this formula, so Un of t acting on some function f, just dilates outside and inside. And for this, scaling factor on the outside is to keep it unitary. And you can similarly define a dilation group on just L2 of the half line by the exact same formula we do in one dimension. And it turns out that these operators actually play very nicely with the Fourier transform that I introduced earlier. So, first of all, the dilation group is a unitary group, strongly continuous, one parameter, so on. So Stone's theorem tells you it has a self-joint generator, which you can explicitly work out with this differential operator here. So you just multiply each coordinate by, and then take a derivative in that direction, and then you add on 1 on 2y for each coordinate you have. And if you actually conjugate this operator by this Fourier transform I introduced earlier, then you can reduce to minus a half times the generator of the dilation group on the half line tensor identity on the L2 of the sphere. So really this dilation operator is somehow a one-dimensional operator, even though it may not be so. And in particular, you have a canonical commutation relation. So the commutator of dilation on the L2 of Rn with half log h naught is equal to I. And so this may be strange to think of how did this factor come to be, but if you were to apply this unitary to the whole thing, the conjugate by it, this would say that dilation on the half-line tensor multiplication by the logarithm of the variable is canonically conjugate. Those two are canonically conjugate. And if you take one more step and do the unitary from the half-line to the real line, then this reduces to an equivalent statement, which is the Dirac operator on the real line is canonically conjugate to the position operator. So there's really nothing interesting about this statement, but that's where the logarithm comes from. So my first theorem. So this was first proved in, there is a version of it in one dimension from 2008 by Sir Richard and Johannes Kellendorf. And this version is for dimension bigger than or equal to 2. And so the first one in 2013 for 3 dimensions by Sir Richard and Raphael Tiedra de Aldecoa. And in 2 dimensions they fixed that in 2021, and then Adam other dimensions this year. So if n equals 2, we have to suppose a dimensional condition, so decay condition for each dimension, and it's much worse in the lower dimensions because of these resonances that can occur. I probably should have mentioned that the resonances cannot occur in dimension bigger than or equal to 5 for just general resolvent bounds for self-joint operators. Alright, so if n equals 2, we have to assume that there are no p resonances. And if n equals 4, we have to assume there are no resonances. But in n equals 3, we can handle the resonances in that case. So it seems that even dimensions causes problems here, but odd dimensions will cause problems later on. So in this situation, our wave operator has a nice form. So it's the density operator plus some particular function of a dilation operator times scattering operator minus 1 plus a compact. And so this particular function is the same in each dimension. So I say this is universal because this function does not depend on the potential at all. And it is half 1 plus tan pi x minus I cosh pi x inverse. And the only thing different for this statement in one dimension is that because of this cosh operator, there's something weird going on because the the 0 sphere is just 2 points. And so there's a weird antipodal map that flips signs of things. So I've not included it here for that reason. It doesn't fit the exact framework. Right. And so it's not obvious at all from this statement, but this already gives us an index theorem in a sense because we can view the wave operator as an element of a particular C-star algebra and then take its image in a Kolkin algebra and compute the winding number and it gives you an index, but that's not the approach I want to do today. So what I wanted to do today is construct some spectral triples and compute an index pairing. All right. So this operator D plus I mentioned before is basically canonical conjugate. So it is equivalent to this Dirac operator on the half line. So if you follow this unitary, then you get these two spectral triples are unitarily equivalent. And so it's just quite a nice fact. And so much more interesting perhaps. So you can take the data CC infinity of the half-line tensor comment operators on L2 of the sphere, L2 of R plus tensor L2 of the sphere, and 2 plus tensor 1. And this defines an odd spectral triple, and so you get a class in K homology. And when S of 0 equals 1, so this what really excludes one dimension from our interest because we don't have S of 0 equals 1 there often. And this S of 0 equals 1 condition will also exclude our resonances in 3 dimensions because it's not 0, not 1 there, it's 1 minus 2 times the projection, which is rather annoying. I haven't been able to fix that. So in this case, the scattering operator will define an element of this odd theory, and so to take these two objects with the wave operator of this particular form that I showed earlier, we can actually pair these and we get an index statement, and so it is not clear that, so sure, we can do a pairing that's equal to something, but the fact that it's equal to the index of W minus is not so obvious. So if I jump back to this form, this operator 1 plus tanh by x over 2, it essentially acts like the spectral projection of the operator d plus, and so, or dn in this case, and so this allows us to compute the index pairing using the formula, the index of p u p minus plus 1 minus p. So this, when p is the spectral projection, so this is close enough to the spectral projection to actually be able to compute the index. And the reason that we need s of 0 equal to 1 to do this is that we need to use like an f of x, g of n argument, and we can't take commutators to get compact remainder terms without that condition. All right, so this is our index pairing, and almost the end of what I want to say. So the next question really is, sure, we have a pairing, we know it's equal to the number of eigenvalues, but how do you actually compute this? And so we have a couple of approaches. And also we have the question of how do we fix up this problem of it not being 1 at 0? And so the problem of not being 1 at 0, the current idea is to, so the operator now lives in a bigger algebra, and so we have to define a different differential operator there, and it is not obvious and it is not easy to figure out which operator to put in this slot instead when you increase the algebra. So we're still working on that. And if you look at the problem here, this D plus, it's always one dimensional. So it's always one summable. And so this means that we can't actually use a local index formula to even compute this, except in one dimension. But in one dimension, I don't have the right scattering behavior to do that. So there's known information about this scattering operator in that it is actually sensitive in some sense to this summability. So it has trace class properties, and so one idea that we have not followed through carefully because it's very difficult is if you take the Cayley transform of the whole problem, switch the roles of the operators, then summability is in the right slot, but then your differential operator is the Cayley transform of the scattering operator, and that's not easy to work with. So I'm not sure what to do there. And so, final slide, I think. So a less common version of Levinson's theorem, which has been known for quite a while, this is in one dimension, says that the number of bound states can be computed as the integral from 0 to infinity of the trace of star S prime. And this looks like a local index kind of formula. And we have a plus half and these half bound states. And it doesn't quite work as a local index formula. So in higher odd dimensions, you don't get extra terms in the trace. The only difference is you subtract off a certain polynomial to make this integral. And it's not obvious that that is a good thing to do or why that works. So my current approach is to compute the spectral flow between the operator H and the operator H, and so using methods of area quantitative and see if that gives you a nice formula that you can actually use to compute this. And so far it seems to be only slightly more general than this and recovers this when you have the right assumptions. So I'm not sure if that's the right thing to do right now. Anyway, that's.
Are there any questions? Okay, to compute this index, so which terms you want to compute? What do you call?
So we want to be able to have a nice, actually computational formula for computing the number of eigenvalues.
Yeah, but I mean, somehow, okay, when your input is V, you plug in V and you want a nice formula in terms of V.
Yes. So like an integral formula in terms of, you can use the scattering operator as well. I'd be happy if that was in there.
Such a formula would count.
Yeah, this is like a useful formula. Yes.
Yeah, so I was wondering, these restrictions on rho, right?
Yes.
The potential has behavior. So can you think of any physical reason that this must be so? That's just the sort of deficiency of the method, or is there some reason that you need this fast decay to be able to compute in this way? I mean, I can understand the mathematical reason, but if there is
another... so it's not physically intuitive why you need these exact values, but it is kind of well known that the more local the interaction is, the better behaved it is. So this is all short range scattering theory. And if you were to do anything longer range, that's a much more difficult theory to deal with. But I don't know any physical reasons why these exact values of rho appear. It's just an artifact of my method.
Any other questions? Okay, in this case, this is the end of the morning session, so we'll have a lunch break until 3, and let's thank you very much.